type HTML empty list, and I have to map that into the right type for a formlet. Okay, so I need to add an applicative functor to its result type. Pure dollar will do that, and then the comp constructor tags it as a composition, so this step is kind of almost trivial. I have to add a name gen functor to it, and pure will do that, and then I've tagged it with comp, and I've got something of the right type to turn into a formlet. So it's very easy to promote operations from any formlet in the composition to the top level. All I do is I either apply pure or I use pure applied to. Okay, and finally, here is the code for generating an input field. And this uses effects in all three applicative functors. I've color-coded them so that you can understand it more easily. So first of all, the outermost one is name generation. We generate a name, and then we apply a function to it. And that actually binds name to the generated name in all the rest of the code, which is a good thing because we need it, and that's why we had to generate names first. The green code is the HTML generation. So I have to generate an input field with the correct name and purely move to the next stage. The final stage is the evaluator, and I can just use that field function that I showed you. So there we are. Generate a name, put the input field in the HTML, and evaluate the result. And if I run the formlet, then it'll give me back, I've defined run formlet to return the HTML itself as a string and the function for processing the result. If I take that person formlet, here's the string that it generates. It's the correct HTML. Same as we saw before, except that we now have generated names for the fields. And if I then call the evaluation function that I get on data that might come back from the browser, then it correctly constructs a person record for me. That's very sweet, I think. Okay, so what have I shown you? I've shown you applicative functors. They're very interesting. They're less powerful than monads. They're less expressive. You can't define bind in terms of the applicative functor operations. But that at the same time makes them more general than monads. There are more instances of functors, and those new instances do really useful things. They're much more composable than monads, which I've used to construct both of these applications that I've shown you. And that means that there's no need for anything corresponding to monad transformers, because we can compose the things anyway. So I think applicative functors are a very nice concept. They're an analogous concept to monads, but they provide a usefully different functionality, and they have a very nice, simple interface. I think they're a real sweet spot in this kind of very generic interface. And I'll stop there.
I see people doing monads and code, for example. They just write the programs in a nice way, but then if they're going to prove things, they just unfold everything and you get the big mess.
Mm-hmm.
Yeah.
Yeah. So when Haskell programmers write monads, they normally don't prove a thing. They normally don't even test monads. But it's at least a good thing to do that. So there are, of course, laws that applicative functions should satisfy. And so you can use those for equational reasoning. Quite how easy or successful that would be, hesitate to claim.
For example, I would want to be able to verify the parser with respect to some grammar.
Mm-hmm. Yeah. I haven't done it, so I can't really say what it's. Why don't we try? Okay, I get the feeling we're all hungry.